Thinking back to our last example, after designing your website, you and your friend decide to go into business setting up sites for others. With lots of practice, you can now work together and design a modest site in 4 hours. Your friend is still a faster worker. Working alone, you require 6 more hours than she does to design a site for a client. How many hours does it take your friend to design a website if she works alone? So similar to the other examples that we looked at, we're going to stay with that same rhythm. We're going to have an amount of time that we're working together. We're going to have our individual rates being summed together, and we're going to equal our one completed job. Now, before you think this is somehow going to change our equation because we're looking for the individual's time as opposed to the group time, it doesn't change how we set it up. It simply will change the path that we take to solve it. So we do know our collective time working. They tell us that if we work together with our friend, it will take us 4 hours to complete the website. So we know that 4 is going to be outside as our time. Now on the insides, we're going to start with our ones in the numerators because we know our rates are going to be unit rates. They're going to have to have been divided. We're talking about one job. How much of the job is completed in a unit of time? But the only information that we have there is, while working alone, I require 6 more hours than the friend. Since the question is asking about our friend specifically, we're going to allow our friend's time to be represented by X. Because we take 6 hours longer than she does, our time is going to be represented by X plus 6. So turning both of those into rate fractions for the two individuals that are working, here's our friend's fraction, and here's our fraction. And you can see why this type of work needed to wait until we got to rational equations, because now we have this binomial denominator combined with the monomial denominator. There's going to have to be some least common denominator work here with polynomials in order to get to a solution. We still want to complete the one job, so we finish it with equals 1. To clean this up a little bit, we can distribute the 4 to the two fractions on the left, leaving the 1 behind. We know at this point that our common denominator is going to be x times x plus 6. That's the factor that's going to get multiplied by each one of the individual rational expressions. So multiplying the first one by our common denominator, we're left with 4 times x plus 6. The x's will knock each other out. Multiplying the second one, we're left with 4 times x. The x plus 6's will simplify. And on the right side, we're going to have 1 times x plus 6, which of course just leaves us with x times x plus 6. You would think that we're going to try to isolate the variable. That's what we did in the last example. We needed our x to be by itself. Unfortunately, because of the presence of this multiplication right here that's going to create an x squared term, we have to go a different route. The presence of the x squared term means that we're going to have to solve this for 0, factor, and solve it using some of our polynomial techniques. The hope is that the factoring won't be too bad and we'll be able to get to a solution that makes sense, but that's still the route we're going to have to go. So unfortunately, all of this needs to be unraveled so that we can start combining terms and moving the terms around to set it equal to 0. I'm going to move everything to the left. I'm going to take everyone and go that way. And the reason is because I want to keep this x squared positive. Sure, I can move it over to the left where there's more terms, and I could subtract away some terms and then multiply by -1 and switch all the signs, but that's not really a necessity. I'm just going to go the way that I know the x squared is already positive. So we're going to leave the x squared, and we know it's going to equal 0. I've got a 6x right here, minus a 4x and minus another 4x, which would be minus 2x. And then we're going to move the 24 over as well, and we get minus 24. Factoring this, we have x minus 6 and x plus 4, giving us two solutions to the equation, x is equal to 6 and x is equal to -4. Now we run into a little bit of a tricky situation because when we solved rational equations, we said When you get a solution, you always want to test it. The fact that we multiplied by the common denominator means we might end up with some solutions that are extraneous. Well, if I test both of these solutions back in the original part of the expression, if I test these two solutions here, excuse the technical difficulties, if I test these two solutions right here, and I put them back into the original equation, they both should work. There's no creating a zero in a denominator anywhere. We should be able to add the two fractions together as needed and end up with the result that we're looking for. The problem with that is that one of them doesn't make sense in the context of this question, not in the context of the rational equation. So if we're looking at this x as a representation of time, we have our friend's time and our time. This solution is no good. Our friend cannot work for -4 hours while we work for 2 hours, which would be +6. We're going to have to use this as our solution, discounting this one because of the context of the problem, not because of any perceived issue with the mathematics. I'm not so concerned with that at this point. I'm more concerned with, are we addressing the context of the problem? So here we're going to have to use 6, which means our friend's time is 6 and our time is 12. So again, set up the exact same way, looking at the time times the individual rates, all of that equal to one job completed, and then using our techniques from previous sections to simplify that equation and solve it using multiplication by a common denominator.